Okay, let's unpack this. We are jumping straight into the engine room of enterprise networking. We've been handed a stack of material that's all based on the Cisco CCNP Enterprise 300-410 concentration exam, which is really just code for the advanced blueprints that build the modern network.
That's absolutely right. And our mission here, it isn't just to, pass a test or review specs. This is more like a knowledge heist. We're going to pull out the most crucial, high-leverage knowledge, the little nuggets, the constants, the rules, the why behind them that really separate an optimized network from a chaotic one.
So think of this as your shortcut. A shortcut to understanding these really complex mechanisms. We're talking EIGRP, BGP, DMVPN, MPLS, and all that deep-seated network security. If you need to get your head around how the big decisions get made in the data center and the WAN, this is for you.
And these are topics that demand absolute precision. We really have to focus on the strategic side of things. Why this number? Why does this one command enable a feature that can save a company millions in bandwidth? We're basically translating technical facts into operational wisdom.
Okay, so let's start with establishing the ground rules for trust. I mean, in any complex environment, you've got multiple routing protocols, and they often disagree. How does a router decide which source of information is, well, the most trustworthy? This takes us right to administrative distance. 80.
80 is the first tiebreaker. It's the network's internal reputation score, and lower is always better. We all know internal EIGRP routes are highly trusted, so they get an 80 of 90. But when we talk about EIGRP external routes, so routes that are imported or redistributed from somewhere else, the trust level drops a lot.
And that drop is very deliberate, right?
Right.
What is that specific default AD value for an external EIGRP route?
It's 170. And that value is anything but random. I mean, if you look at the competition, OSPF internal routes have an AD of a 110. A static route is usually 1. The fact that EIGRP external routes are all the way up at 170 is a strategic choice. It's baked into the architecture.
So what's the strategy? What's the implication of setting it so high?
It creates a clear hierarchy of preference. By setting it to 170, the network guarantees that almost every other valid routing source, whether it's OSPF, RIP, ISIS, even a local static route, is going to be preferred over some route that got redistributed into EIGRP. You trust your natively learned stuff first. It's a defense mechanism, really. It stops bad information from the outside from leaking in and messing up your stable internal paths.
That distinction between internal and external info is so critical. Okay, let's pivot from trusting the source to actively influencing where traffic goes, specifically with BGP. BGP is, the protocol of the internet, but it's also huge for internal traffic engineering. So we're looking for the attribute that influences outbound traffic selection, but strictly inside your own autonomous system, your AS.
This is a classic BGP traffic engineering problem, and the answer immediately defines your boundary control. If you want to influence your internal BGP speakers, your IBGP peers, without messing with your neighbors on the outside or eBGP peers, use local preference.
And here's where it gets interesting for me. Why does local preference keep that influence internal? How is that different from, say, using AS path prepending?
It's all about the propagation rules. Local preference is an IBGP-only path attribute. When one of your IBGP routers gets a route with a certain local preference, it passes that value to all the other internal BGP routers. But, and this is the crucial part, when that route leaves your AS and goes to an eBGP peer, the local preference attribute is just stripped off. It's not advertised, it's contained.
So if I were using AS path prepending, I'd be trying to influence my neighbor to send traffic back to me a certain way. But with local preference, I'm just telling my own internal routers, hey, for traffic going to this network, use router A as the exit, not router B.
You've got it. Local preference lets the network architect manage their own congestion, their own load distribution, completely independent of the global routing table. You don't disturb any of your external peering relationships. It's like the ultimate internal thermostat for your traffic flow.
Okay, so we've covered trusting routes and influencing traffic. But what happens when the network itself starts to, doubt its own choices? You need an ironclad guarantee against routing chaos. And that brings us to the core mathematical rule of reliability in EIGRP loop prevention.
And this is really the genius of the EIGRP algorithm. Unlike the old distance vector protocols that just used hop counts and timers, EIGRP uses what's called the feasibility condition to guarantee a loop-free backup path.
So break that rule down for us. What's the specific requirement for a route to qualify as a feasible successor, a safe, loop-free backup path?
It all comes down to two metrics: the reported distance, or RD, and the feasible distance, FD. The RD is the distance that your neighbor is advertising to you. It's what they're telling you the path costs from their perspective. The FD is your current best metric for that path, your total cost.
And the mathematical guarantee is?
The reported distance of the neighbor has to be strictly lower than the current feasible distance of your successor. Think about it. If your neighbor's cost to get to the destination is less than your best cost, there's just no way that traffic can loop back through you. That neighbor has a better path that doesn't involve you. That little inequality sign, strictly lower, is the whole mechanism. It prevents routing loops before they can even form. It's instantaneous reliability.
That is a perfect example of architecture driving stability. Now, loop prevention isn't just about dynamic protocols. It's also super critical when you're forcing two different protocols to talk to each other, what we call mutual redistribution.
Right. If you have EIGRP and OSPF talking, it's so easy for a route that started in OSPF to get pushed into EIGRP, and then EIGRP, thinking it's a new path, just redistributes it right back into OSPF, and bam, you've got a costly, nasty routing loop.
So you need a way to mark a route. To say, hey, I came from here, don't let me back in.
Right.
What's the best defense mechanism inside a route map for that?
Matching route tags. Tags are essentially just metadata. You set up the route map doing the redistribution to stamp each route with a unique tag. Say, all OSPF routes going into EIGRP get tag 100. Then on the other side, the route map controlling EIGRP routes trying to get back into OSPF just looks for tag 100 and says, nope, access denied. You're already one of us.
It's like route accounting. It's clean, it's precise, and it solves the biggest headache that redistribution used to cause. Okay, we've established stability. Now let's talk about building the scalable enterprise fabric. How we get speed, protection, and the dynamic connectivity all working together.
Let's start with speed and specialized forwarding. That immediately brings MPLS to mind. When a packet enters an MPLS network, it gets a label. And from that point on, traditional IP lookups just get bypassed for efficiency.
Right, and that efficiency, it needs its own dedicated data structure. We're not using the massive routing information base, the RIB, which is the control plane. We aren't even using the normal forwarding information base, the FIB. We are using the LFIB.
The label forwarding information base. And the key distinction here is that the LFIB is purely a data plane structure. It's used by the label switch routers, the LSRs, and it only contains label-to-label mappings in the outbound interface. That's it. It lets the router just read the label, swap it, and push the packet out, totally bypassing those slow, complex IP address lookups. It's the express lane.
That's the speed component. Now, protection. Every modern router has to protect its own brain, the CPU that runs the whole show. If that CPU gets overwhelmed, the entire network fails. The solution: control plane policing.
CoPP, as it's known. And its main goal is not to protect traffic passing through the router. Its job is to protect the CPU from denial of service attacks by rate-limiting traffic destined for the router itself. We're talking about things like SSH sessions, routing updates, or ICMP pings.
So if some attacker floods the router with thousands of malicious BGP updates, CoPP just steps in and throttles that traffic. It makes sure the legitimate updates still get processed and you can still log in and manage the box. It's operational insurance.
It guarantees that even under a heavy attack, the routing protocols stay up and you can still manage the device. Resilience is everything.
Speaking of protection, let's look at IPv6 for advertisement or ROA messages for hosts to figure out their network prefix and gateway. So if a rogue device starts sending fake RAs, it can break connectivity for the whole network segment.
And the layer 2 switch feature you need for that first top security problem is IPv6 RA guard. You just configure this on your access ports, and the switch starts filtering out any unauthorized or just plain invalid router advertisement packets. It makes sure that only your sanctioned, legitimate routers are allowed to broadcast that configuration data. It keeps the whole addressing ecosystem honest.
Okay, let's shift to how we handle dynamic site-to-site connectivity efficiently, specifically DMVPN Phase 3. DMVPN is a great hub-and-spoke solution, but Phase 3 is all about moving beyond the hub after the initial setup.
Yes, the goal is direct spoke-to-spoke tunnels for low-latency communication. And this needs active signaling from the hub. When Spoke A wants to talk to Spoke B, it first goes through the hub, and the hub has to tell them, hey, you two should talk directly.
And the specific next top resolution protocol NHRP command that you need on the hub to trigger that is EENHRP redirect.
Correct. That command tells the hub to send an NHRP redirect message back to both spokes.
This gives them the real public IP address of their peer, and that lets them dynamically build their own dedicated high-speed tunnel between each other.
They completely bypass the central hub for the rest of that data flow. It basically turns a hub-and-spoke network into a mesh network, but only when you need it.
That is some incredible optimization. And optimization brings us to our next point. Policy-based routing, or PBR. PBR is powerful. It lets you override the routing table, push specific traffic to a firewall or whatever. But PBR is static, and that's a major weakness.
Oh, it's a huge weakness. A static policy pointing to a next hop IP that suddenly fails just creates a black hole. Traffic just gets sent off to nowhere because the PBR policy has no clue that the link is down. To make PBR intelligent and reliable, you have to integrate it with IPSLA.
IPSLA service level agreement. So this lets us actively monitor the health and performance of that next hop address.
Precisely. You set up an IPSLA probe, like a constant ping or UDP echo to the next hop that's in your PBR policy.
Yeah.
If that probe fails, the PBR policy gets dynamically withdrawn. The router just deactivates it using tracking objects that are linked to the SLA status. Then the router just falls back to using the normal routing table. It guarantees traffic always has a viable path. It makes the static policy responsive.
We have covered a tremendous amount of ground, from controlling global influence with local preference to building those responsive tunnels with NHRP redirect and guaranteeing reliability with IPSLA.
And we really focused on the precision that's required. Let's wrap with one last essential nugget. This one is more about operations, not just routing. syslog severity levels.
Oh, this is a crucial fact for any network engineer setting up monitoring. If you want to capture messages that give you standard operating context, the non-critical details, the informational level, what's the number for that severity level?
The severity level that corresponds to informational is 6.
And that setting is powerful because logging trap levels are inclusive, right? If you set the trap level to 6, the device exports logs of level 6 and all the higher severity messages. So all the more critical ones, like errors, which are level 3, warnings at 4, notifications at 5, they all get sent to your log server too. It's pretty much the standard baseline for robust network monitoring.
We talked about how critical the LFIB is for high-speed MPLS forwarding and how we use IPSLA to track the reliability of next hops for PBR. So, given that the LFIB is the absolute key to fast label switching, how might advanced sub-second monitoring protocols, I'm talking about things like bidirectional forwarding detection, BFD, or maybe enhanced IPSLA, how could those be used not just for routing, but specifically to validate and manage the stability and health of the label switching path itself? That's the frontier of optimization we've just touched on.
Until next time, keep digging and keep optimizing your fabric.